Okay, this is ECE641 today, and today we're going to be finishing up with the probability and moving on to the first chapter on modeling, but I probably should cover a few quick topics. One is that I think, and it's totally my fault, that there's a little bit of confusion about the homeworks. And because I forgot to update the I forgot to update what is the thing called? A laptop. The syllabus, right. So this is the course web page, as you've all know and love. And then you go to the syllabus under the course, but I forgot to update the dates because I was still a little unclear. Okay, I should have done it. I'm going to blame it on the pandemic. So basically the idea, so we don't have Labor Day off. But the idea is that every Friday you have a homework due, except for when labs are due. Or actually, even when labs are due, but the difference is just that there's exams. And even the exam, we're not exactly sure what we're going to do yet. See, there's an exam on a Friday. Okay, so let me work on the syllabus. But the important thing is you should have you should be handing in homework assignment 2 today. And homework assignment 2, you can get by, so the actual homework assignments are here, right? So this tells you, so you do the first 5 problems, you were supposed to hand that in last Friday, and the second half of them today. Now, I understand some of you may have had problems with them, and I was going to wait until today, and maybe on Monday, then we can go over some of them, okay? I was also trying to think about maybe having a Zoom recitation session. I don't know. I had a little bit mixed feelings about that. I wasn't exactly sure whether that would work for everybody or not. I was kind of looking to see how things were going a little bit. But yeah, but maybe I want to try to cover as much as I can in regular lectures as possible. So I can try to do some problems in lectures. And I think I've given, and I try to give you, if you ask me about the problems that are giving you difficulty, then I can just try to work them into the lectures, okay? But then if there's still questions, and then of course I'm going to hand out solutions. But then if there's still questions, then maybe we can do an additional Zoom recitation or something like that. And I can also, of course, you can email me and I can answer questions, or if you want, I can Zoom individually with people to answer questions too. Maybe what I could do is set up a regular office hour, and anybody can then Zoom into it. Maybe that's the way to do it, and ask the questions so that other people can listen while questions are being asked. Maybe that's how I'll do it. I've been sort of struggling with trying to figure out how to do this in the best way. Okay, so are there any other questions? Okay, so I want to talk about Bayesian Estimate. We talk about frequentist estimators. I noticed also that there was a problem that the blackboard was hard to see when the projector was on because of the automatic gain control and the video camera. So I'll just mute it while I'm not using it. So Bayesian. Okay, so in the Bayesian, so the frequentist viewpoint, so the goal is to have an unbiased estimator. The idea is that you make minimum assumptions. And the classic example of a frequentist estimator is when you have IID Gaussian. So frequentist estimator would be like you have xi r n mu, say sigma square. I'll just do the one-dimensional case. We did the general multivariate case before. So then you'd have like for I equals 1 to n, okay, and these are IID. And then theta here is mu and sigma squared. Those are the unknown parameters, right? And the so then the MLE, the ML estimate, is equal to theta hat is equal to the arg min over theta of minus the log of p sub theta of x, where this is the vector. And the different arg min is something I'm going to use a lot in this class, and it's pretty commonly used these days in all kinds of applications. But the idea of the arg min is different from like min. Okay, min tells you the value of the minimum value of the function. Okay, minimizes the function. So arg min tells you the location at which the minimum occurs. So if you have some function like this, okay, this is the min over theta of f of theta, and this is the arg min over theta of f of theta. So if this is, so the arg min is the location of the minimum. And the location may not be unique. So arg min sort of presupposes uniqueness. So it's a little bit, you have to be careful about that. But for many of the problems we deal with, the solution will be unique. If the, well, later we'll find out if the function is convex. So like the arg min across the United States, the continental United States of altitude is Death Valley. But the minimum is minus 300 feet or something like that, okay? So that's the distinction. Now the, okay, so now, okay, so now this is the frequentist viewpoint. In the Bayesian viewpoint, it's too bad that they don't give you something to attach this with so it doesn't get in your way all the time. Using up good Blackboard space. Okay, well, this is just not working. Okay, that's not going to stay there, I bet. Oh, it did. Okay. So, in the Bayesian viewpoint, the idea is you have y, some observations, okay? And, oh, I guess, oh, maybe I should have made these y's. Oh, by the way, what is the maximum likelihood estimate? You'd have to do the calculation. So, the mu hat is the MLE estimate for this is what? Yeah, it's 1 over n. From I equals 1 to n of yi, right? Mm-hmm. And then the standard deviation, see, when I put a hat on something, it usually indicates that that's an estimator for the thing without a hat. So this is a random variable. That's not a random variable. So this is 1 over n times the sum from I equals 1 to n of yi minus mu hat squared, like that, which is also equal to, well, okay. I mean, I can write this other ways, I guess. I can write it, and if we have sufficient statistics, we could have B and S. S here is the sum over I of yi transpose, and B is the sum over I of yi. So then this would be equal to S over n minus b transpose over n squared. So you can write it in terms of the sufficient statistic. And this is b over n. Okay, so you can write it in terms of the sufficient statistic. But you should do this calculation. Doing the calculation for the 1D case is relatively simple. You have to differentiate with respect to mu and sigma. But doing it in the multidimensional case is harder. Yeah, and then I also told you this estimator is biased, okay? Because the expected value of sigma hat squared given sigma is actually equal to, it's not equal to sigma, okay? It's actually going to be equal to n minus 1 over n times sigma squared. So the maximum likelihood estimate can be biased, and this one is. And that's why everybody, the conventional formulas you often see, divide by n minus 1, because then that's an unbiased estimate, and it actually has lower variance. So, no, it doesn't have lower variance, but it has lower mean square error, okay? So it's uniformly better. Okay. So, okay. Now, okay. So with the Bayesian estimate, you have y, and y is computed is conditionally dependent, conditionally distributed, given some probability distribution in x. But x here is also random, and this is the prior distribution. Okay, and so the goal is now you want to estimate x given y. Okay, so the probability distribution. Okay, my notation here is horrendous. I'm going to do exactly what I told you should not do. Okay, okay. You shouldn't do this, okay? Because this function and that function are the same function. But I'm kind of using the variable names that I plug in there to distinguish them. So let me not do it, because it really is the wrong thing to do. So I'll write a little subscript on the here to distinguish them. So using Bayes' rule, this is the probability of y given x times the probability of x divided by the probability of y, okay? Now, the probability of y you can calculate by integrating this thing, okay? So, but, okay, but divided by the probability of y. But, you know, let me give you some intuition here, because the idea here is really pretty simple once you get it to click into your brain. That this thing here, okay, this thing here is really the joint probability of y. It's the joint probability of y and x. Oh, it's the joint probability of y and x, right? So the point is that the joint probability of y and x and the conditional probability of x given y are the same as long as you just normalize it so it integrates to 1, okay? That's the thing that's kind of interesting. So you put, you just times 1 over z, okay? Where z now is a function of x. But you can pretend that you don't. So in other words, if you look at this function, f of y is equal to p of y. Okay, this is another thing that I'll complain bitterly if you do on an exam, okay? I'm just doing it this one time, but don't make a habit of it, okay? You should always have to have the same letters on the left and the right side of the equation. I hate it when people write things like this, okay? But what I'm saying, I'm just trying to say here that if you think of this function for 1x, so you just think it as a function of y, okay? Then this integral, then if you divide by z here, to get P of y, okay, so this is P of y given x. To get to this is a conditional, this is a probability distribution on y. So it has to integrate to 1. So this z here, okay, this z here is, this z here is got to be equal to whatever this whole thing here is. Call this f of x. F of y, I'm sorry, f of y. It's the integral of f of y dy. So this is just a normalizing constant. But in a lot of applications, if you have the functional dependency, it's just not properly normalized. That's not a big deal, because you can always go back and renormalize it. So you calculate some function, that's your probability density, but it's unnormalized. So then you integrate it, and you divide by that integral, and that normalizes it so it integrates to 1, right? It's like having some kind of unnormalized quantity. You can always normalize it in the end. And we'll use that trick a lot, okay? That's a very important trick. And that's what Bayes' rules is saying. Bayes' rule, this dividing by P of y is just a normalization factor that makes sure that this integrates to 1. It's the thing on the top that's really the most important, okay? So, okay, so that's Bayes' rule. So then so there are different estimates. I only gave you the maximum likelihood estimate. Obviously, there's lots of other estimates for frequentist frameworks too, but the maximum likelihood is one of the more commonly used ones. There's a lot of different estimates. So in a Bayesian frame, now the problem with the maximum likelihood estimate is that it's hard to say any estimator is the best estimator. Once in a while, you have a situation where one estimator is, I mean, okay, it's hard to say that any estimator is the best, okay? Because it's like this clock here that I told you last time. If it's 1:37, okay, then that clock is exactly right, okay? The rest of the day, it's wrong, because it's broken and it always says 1:37. So, but it's hard to say, you can say, well, I don't like that clock, it's a really bad estimator of the time. And you're like, but if, like, I'm a person who thinks 1:37 p.m. is like the most important time of the day, and that's the only thing that I care about, then I think it's a great clock, because it always gives me exactly the right time at 1:37 p.m., okay? So the point is that it's hard to say categorically that it's a bad estimator of time, even though conventional wisdom say it's a terrible estimator of time, okay? Because it is, because it's hard to say, because you can't pick an estimator which is uniformly, there's no estimator that's uniformly best at all times, okay? Because even the worst possible estimator is great at the one time it picks, okay? So the fundamental problem is that the performance of your estimator is a function of theta. That depending upon what theta is, the unknown, your estimator may be great or terrible. Once in a while you can find, so that's where unbiasedness comes in. Unbiasedness is a constraint you introduce. So you can say, well, if I only look at unbiased estimators, then is there one estimator that's best? Even they're usually not one estimator that's best. But what can happen is once in a while you can have what's called a uniformly unbiased estimator, uniformly minimum variance unbiased estimator. So once in a while you get lucky and there's one estimator that's better than all other estimators. But even then it's not really very satisfying, because the problem is unbiasedness is a very strong constraint, which is going to actually be undesirable in a lot of cases. So the upshot is that the frequentist side of the world is beautiful. It's pure. But it doesn't give you an answer to anything, okay? There used to be a TV show on when I was a kid called what the? Oh, I've lost it, okay. Oh my God, it was Kung Fu with David Carradine, okay? I'm sure you've never heard of it, but it was very philosophical, and everybody thought it was a great show. And you went on, and the main character, David Carradine, would go to his mentor and say, "What should I do?" And the mentor would say, "Grasshopper, think deeply about the meaning of the sun and the stars and the relationship of this to that." And then David Carradine would walk away and have absolutely no idea what to do. So usually he'd beat up the bad guys, and that's how the show would end. But, okay, so the point is, this is all beautiful, but it doesn't tell you what to do. It leaves a lot, so you have a lot of, it doesn't say anything that's wrong, but it really doesn't give you a clear path forward, okay? The Bayesian viewpoint, on the alternative hand, actually tells you exactly what the distributions of everything are, and now you can find optimal estimators. It's unambiguous. There's a best estimator, and you know what it is, and there's nothing to argue about, okay? Over here, there's great uncertainty. It's like Zen, okay? But over here, it's very clear-cut. Just do it, okay? Now, the problem, though, is that in order to achieve that great certainty, you have to make very strong assumptions about the world that offend people, okay? So you're like, how do I know that X is distributed like this? So some people find that just absurd, and they can't accept it. This is kind of like, in my view, this is sort of like you're going, this side's a little more evil, you might say. This side over here is more pure, okay? But the problem is this purity leaves you with a lack of an understanding of what you have to do to solve your problem. Over here, you make these strong assumptions. It's unpure. It's difficult to justify. But at least you know what you have to do, okay? Now, so the big concern is usually the prior model, okay? So now, once you made that choice, then you also have to make some other choices. You do have to decide what kind of risk. You usually have to adopt some kind of, well, what today they'd call as a loss function, and the associated risk. And then, so if your loss function, okay, a loss, I'll call it the loss function, because with machine learning, that's what they call it now. So you have mean squared error. So the mean square error loss we have as d of, so d of, so the mean square error loss is, x hat, I forgot to write here that. So x hat is again going to be a function of y. That's your estimator, okay? So x hat minus x norm squared. So here, and t is going to be, okay. T is your estimator, so you have to choose your estimator. So usually what you want to do is you want to minimize this over t. So you want to choose the t that's best, okay? And this is the minimum mean square error estimate. It turns out that the minimum mean square error estimate always has the same form. X hat minimum mean squared error is equal to the conditional expectation of x given y. It's always that. Now, but there's problems with minimum mean square error that it's not always a desirable estimate, okay? Okay. I'll erase this, because I want to leave out the frequentis piece there to contrast what I'm doing. Then, another one would be, another possibility is minimum absolute error. So then your goal is to minimize x minus x hat. This would be in like a scalar case. In a vector case, it could be minimum. It could be an L1 norm. So you take the sum of the absolute values, and then so here x hat is equal to the conditional median. So the conditional median, it means you take the posterior distribution and you find the point integral from minus infinity to x hat dx that's equal to 1/2. So in other words, it's a point at which the integral is half of it, that half the mass of the posterior distribution is on one side or the other, okay? But the, I'm running out of space, so I'm going to have to use it. But the most commonly used Bayesian estimate, and the one that we'll talk about most in this class, is the map estimate, which is maximum a posteriori. Okay, and it's a very intuitive estimate, but it has a lot of deficiencies. But it's easy to compute, relatively speaking. Is you take x hat is equal to the arg max over x of the x given y. So it's the value of x that occurs with highest probability given knowledge of the data, okay? So if you rewrite this, it's equal to the arg min of the negative log of p of x given y, right? But I know I just wrote this down, but is it right if I erase it? It's not going to carry off too much. This is all in the notes, but because there's a calculation I want to go through. So you have the log of p of x given y. That's equal to the log of p of y given x times p of x over p of y. By the way, the reason that it's often useful to use Bayes' rule is that for a physical system, it's often the case that p of y given x is a more natural thing to calculate because that represents the output of the sensor, right? So this thing, so this is the posterior, this is the prior distribution of the unknown observations. This is usually known for physical reasons based upon the physical properties of the sensor. And p of y, we're going to see we don't really care about, okay? So what happens is this becomes the log of p of y given x plus the log of p of x minus the log of p of y, okay? So what happens then is that I'm minimizing this thing over x. So this thing becomes the arg min over x of minus the log of p of y given x minus the log of p of x minus plus the log of p of y. But I'm minimizing over x. So if I'm minimizing this expression over x, this thing doesn't matter because it's not a function of x. Now, if I were actually computing the min, it would matter because it would shift the value of the minimum. In other words, if I took the entire United States of America and I jacked it up like 1,000 feet, then Death Valley's altitude relative to the ocean would change. But the position of Death Valley wouldn't change, okay? So if I move the function up and down, the minimum changes, but the argmin does not change. So this has no effect on the argmin, okay? That's another trick we'll use a lot. So I can get rid of this term, Does people understand that, or at this point, does that make sense? Okay. So I get rid of that term. So this is the map estimate. You're going to see this all the time. The idea is that, so what is this? This is telling you, you're picking an x such that this thing is the log likelihood, if you remember. The log likelihood is the thing we maximized, or the negative log likelihood is the thing we minimized to do the maximum likelihood estimate, right? So if I remove this term, then this is, if I remove this term, then x hat is something else. Does anybody know? Excuse me? Yes, it's the maximum likelihood estimate. Oh, very impressive. Okay. Okay, so everybody, okay, tune in again. Okay, so the idea, this is the map estimate. The map estimate, there's two terms. There's the forward, and this is the prior. Now, minimizing this is the same thing as maximizing. Okay, minimizing the negative is the same as maximizing the positive, right? So if I minimize this term, I'm maximizing the probability, the prior probability. What does that mean? It means I'm picking an x which seems like it was probable to have occurred, okay? That's a probable x, right? You don't want to pick an x that the probability of it occurring is ridiculously low, right? It's like saying, oh, I don't know. Excuse me?
Seeing lightning strike on a sunny day.
Yeah, exactly. Thank you. You're really helping me there. Because the thing is that, you know what? I mean, it's like you know, somebody says, okay. Like I ran into a friend of mine. Guess where I ran into my friend? And you say, on Pluto. And they're like, well, no, obviously not. Because what's the probability of your friend being on Pluto? Okay? Okay, so this penalizes things that are super unlikely to have occurred, like lightning strike on a sunny day. I mean, you can have a lightning strike on a sunny day. It happens, okay? But not very often. So this tells you, pick something which is probable, that like before you know anything, before you hear the data. No data, just based upon like your experience in the past, okay? This tells you, pick something which actually fits the data. Now, if I set this to 0, all I'm doing is fitting the data. So this is just like the maximum likelihood estimate. If I pretended x was not random, if it was just unknown, then this is the maximum likelihood estimate. So the difference between the map and the MLE is that the map estimate includes this prior term. So it says, don't just fit the data, also pick something that's reasonable. See, that's the thing about the MLE. It's the frequentist side of the world. It's pure. They're like, they have no preconceived notions about how the world should be, okay? Oh yeah, there was a whole bunch of lightning yesterday while the sun was out. No, it's like a naive person. You went to them and you said, oh, I ate 50 hot dogs yesterday. Oh, that was nice. Was it good? Like, you'd be like, oh, come on. You didn't eat 50 hot dogs, okay? Because it's just not, like, it doesn't seem likely. It's not probable. The prior distribution is low for that. So the map estimate is more jaded. It's using its prior information about the distribution. Now, you'd say, well, oh, I'd rather not do that. But the problem is, often you don't have any choice, because there's simply not enough information. So there might be like an infinite number of possible solutions. So how am I going to pick between them? Well, I got to use some auxiliary information. So that's what the difference is between the map estimate and the MLE. Okay. Now, here's some rules of thumb. So when do you use, so over here I'll put MLE and map. By the way, you can see this on the projector, right? I'm not writing off the projector screen, right?
No, you're good.
Okay, so MLEs use when okay, M is much greater than N. So here, N is a dimension of theta or dimension of x, okay? So N will be the number of unknowns in my, I'll use P, I'm sorry. I'll use P. And M is the dimension of y. It's the amount of data, okay? So if I have a lot of data and only a few unknowns, the MLE is a good choice. If P is much greater than M, then I use map. Okay? This is just a rule of thumb. First of all, if P is greater than M, usually the MLE estimate is not unique, at the very least. Okay? So you have to do something. Okay? So a map is a way of getting around it, or Bayesian, more generally. Okay? I should also say that you know how these things are. Nobody ever admits defeat, right? So, and nobody's defeated here because both frameworks are useful, okay? But the Bayesian framework became popular it's hard to say that it's actually newer. That's probably actually not really true. Both of them sort of developed separately, but it's become more popular in, say, the last 20 years, okay? So maybe 30 years, and a lot of frequentist people didn't like it. They found it they found it very difficult to accept because they can't accept this prior distribution concept, right? So you know, and what ends up happening is that the frequentist viewpoint is good for doing certain things, and the Bayesian viewpoint is just good for doing certain things. But what ends up happening is if your technique's not good for doing something, then you try to fix it up, okay? Because nobody ever wants to admit defeat. So there's adjustments to the Bayesian framework. They have things like penalized maximum likelihood estimates that sort of capture what you can get with the map estimate. But the map estimate, in my opinion, is sort of the more natural viewpoint for adopting that, okay? It's built into its whole philosophy, okay? So the other thing is that I guess this is the main case. This is the main determining factor. That so, for instance, if you have 1,000 measurements and you have a mean and a variance, use the maximum likelihood estimate. But if you have like 100,000 measurements and you have 1 million unknowns, so you have to reconstruct an image from 100,000 measurements, you have way more measurements, you have way more unknowns than you have measurements. So then you need a Bayesian framework, okay? And then I want to show this example 2.7 because you asked for that. Okay, so a classic example of a Bayesian estimate is the minimum mean square error I'm trying to figure out if it's faster for me to, given the time limitations. So you have, example 2.7. So X is distributed as N0 Rx. And y is distributed as n. Oh, let me write it this way. I'm sorry. Y equals x plus w. This is going to be like a classic example of a simple estimation problem. So y is our observation. This is the signal we're trying to recover, and that's noise. And the noise and the signal are assumed independent. So w is distributed, usually it's zero mean, right? So it's zero mean with covariance RW, say, okay? And x, see, we could assume that x was just not random, okay? So if I did MLE estimate of x given y, what's the MLE estimate of x given y? Well, we know what the distribution y is because x is independent. So let's say this is assumed non-random, okay? If it's non-random, what's the maximum likelihood estimate of x given y? It's just y, okay? So x hat MLE is just y. So we make the measurements. We know they're noisy. We go, oh, but my maximum likelihood estimate is just my measurement. So we don't process the data. It's sort of dissatisfying because you feel like, well, I would like to be able to do something to make it better, right? But there's nothing you can do because you have the observation. If you had multiple observations of the same y that were independent, you could average them. But if you only have a single observation, you're pretty much stuck. What are you going to do? That's the maximum likelihood estimate, okay? Now, if you have, so the map, or I'll say the minimum mean square error, okay? For the minimum mean square error, if we calculate the posterior probability of x given y, okay, then we can the map from this posterior probability, we can calculate the conditional expectation of x given y. Now the calculation here is a little tricky and very important, so you should definitely go through it, but I don't think I'm going to be able to do it here, okay? But what you basically do is this. You go, okay, you take advantage of the fact that, okay, y and x are jointly Gaussian. Because x is Gaussian, x is conditionally distributed as zero mean covariance x. You need this for the Bayesian case, right? For the MLE, technically speaking, you can't do MLE here because MLE only applies to when x is not random, but we just pretend it's not random for the purposes. Okay, so the joint distribution, so you want to compute the posterior distribution. So the posterior distribution of x given y has to have the form, the conditional expectation of x given y, okay, y is zero mean, so it has to have the form a times y for some a, okay, and okay, there's a number of different ways to do this, and okay, I'm running out of time. Okay. There's a way to do this calculation, and it's important, but I don't have enough time to do it. What you do is this. You calculate the probability distribution of x given y, okay, is equal to the probability distribution of y given x times the probability distribution of x, right? We know the probability distribution of x, it's 1 over z times the exponential of -1/2 x transpose rx inverse x, right? And the probability distribution of y given x, we know what that is too. it's going to be 1 over z, this is a different z, exponential of minus 1/2. This is y minus x, right? Transpose. Now, the conditional distribution of y given x is really going to be distributed as x plus something which is a distribution that's Gaussian with a covariance of w. So this thing here is going to be rw inverse y minus x, like that, okay? Is that clear? Maybe that's not clear. If that's not clear, you need to go off and think about why this is true. That's an important, like writing down the conditional distribution of y given w. I know the conditional distribution of y given w because of this equation here. I know that y is formed by taking x and adding w to it, okay? And w is distributed with covariance r, so that's got to be the covariance of the difference between y and x, okay? So now I can put this, if I take the log of p of x and y, I get something that looks like minus 1/2 x transpose rx inverse x plus 1/2 y minus x transpose rw inverse y minus x, okay? I get a quadratic form. Can you see that there, by the way? I don't know why they put this stupid thing here. They have no respect for the blackboard. Okay, so now what you do is you use the fact that these both things are have a quadratic form. In the notes, it shows how you can do the calculation. Because there's no way I can go through this calculation in class. This is a perfect example of why, what I mean when I say you have to read the notes. There's just not enough time for me to go through the calculations myself. Right here, see this messy calculation? Go through this, okay? This is the calculation that you use to calculate the posterior distribution. Basically, what happens is you know that the posterior distribution the log posterior distribution has to have a quadratic form. And you also know that it has to equal the sum of these two terms because it has to equal this. So you differentiate things on both sides, you set constants equal, and you get the mysterious, the result pops out, okay? And when you do the result, it comes out to be like this, and then you get this, okay? Go through this calculation carefully. So this is the posterior mean and variance. But let me go to 2.7. So this is the posterior mean. So you're going to have to just walk through these calculations carefully, step by step. If you have a question about it, ask me. But if I just can't go through the calculations myself in class because it's too time consuming. But let me try to give you just a little bit of intuition. Yeah?
I have a question about this.
Yeah, okay.
To understand the mean of x given y, don't you have to already have your answer that you're looking for?
No, you only have to have y. Okay, so this is the conditional expectation. So this is the conditional expectation of x given y. So this is the minimum mean square error estimator of x given y, and it's a function of y. So you basically take y, you multiply it by this crazy matrix, okay?
How do you obtain that crazy?
You know what this is because it was given to you. You're asking excellent questions, okay? My answers may sound flippant, but they're not meant to be, okay? It's just that it's a hard thing to understand. You know the covariance of x. That was given to you. You don't know x, but you know its covariance. because you were told the distribution of x.
Okay.
You were told the distribution of w. That was given to you. Before you started the problem, that was how I set up the problem. I said, oh, we have noise with this covariance, and x we're assuming zero mean with that covariance. Right? So those are available to you. You know them.
Okay.
Okay? And so you know them. You know this, so you know these matrices, you can invert that. The interpretation of this is what's called a Wiener filter, because this is a whitening operator, and that applies to the covariance. I mean, the magical thing comes out. There's a couple of different ways to write it down. The other thing that's super interesting here is the conditional variance of x given y doesn't depend on y. That means that your uncertainty in your estimate is invariant to the data. That's really disturbing. It's not true in most problems. In most problems, knowing the observations tells you something about your uncertainty. But if everything's Gaussian, that's not true. If everything's Gaussian, you can pre-compute the uncertainty in your estimate before you actually collected the data. And that just is an example of why Gaussian assumption is usually doesn't hold in many physical experimental problems. That some places you're going to have good estimation accuracy, in other places you might have bad. Right? Do you want to think about this? You're looking at me as if you totally don't believe me.
No, I believe you. It's just you have to have an understanding of x before you can estimate x. Right?
You have to have a model. Yes, and here this cuts to the very core of why the Bayesian approach is evil. Because you've made assumptions about its distribution. It's a self-licking ice cream cone. But it's a self-licking ice cream cone that we have to use whether we like it or not. Because it's so powerful. Because in the beginning, when I showed you that bias variance curve, if you want a zero bias estimate, its variance is infinite. That's a cost that most people are not willing to pay. So maybe go back and relook at that stuff. So that's why these simple ideas are really the most important thing you'll take out of this class, in my opinion. Okay, but please, I beg of you, read the notes and the chapter in detail. Work the problems. You're supposed to hand them in every Friday. I'll send an email reminding everybody of that because it's my fault. Things were a little weird this semester. Okay? All right. Thanks a lot and have a nice weekend. Okay?